Okay, so we're working on a set of notes that has, or at least a topic that has three parts to it. We're talking about limits as x approaches infinity, limits as the function approaches infinity, and three limits that you have to memorize. Okay, so the first part of this is going to be about limits as the x variable approaches infinity, right? Okay, so usually this symbolically comes out as the limit as x approaches infinity, or sometimes you'll have the case where x is actually going the other way and approaching negative infinity. Okay, so there's a technical definition here, which is that for every, so that's that upside down A again, for every epsilon greater than 0, so we again have this two-player game. You have an epsilon player who's picking a number bigger than 0. There exists, so that's the backwards E, and there's the second player. He's going to pick an N, so this time instead of picking some number bigger than 0, he's just going to pick some real number, such that, okay, if the x value is bigger than n, then the distance between L and f of x will have to be forced to be less than epsilon. If this is the case, then the limit as x approaches infinity of f of x is this letter L. Okay, so this is the technical definition of a limit as x approaches infinity. Okay, so again, it's a little bit technical and kind of hard to grasp. So let's try to put a picture to this. Okay, so for our picture, we're going to kind of work in just the first quadrant here. And we're going to create a function. We'll call this thing f. And it's going to look like as f goes along, it seems to be approaching something as we go off to infinity. Okay, so we're going to say, let me grab maybe a different color here. We're going to say that this thing approaches some value. We're going to call this value L. Okay, so as x goes off to infinity, it's going to go with L. So the epsilon player picks some value bigger than 0. Okay, and we're going to go and build a tube. We're going to say, here's the value epsilon units above L, L plus epsilon, and here's the tube epsilon units below L. So L minus epsilon. So what the other player needs to do is now pick a value. Okay, so let's pick a value n. So this is an x value. So that everything bigger than n causes the function, so that's the green thing, right? The function to be inside the tube. So the function is within epsilon elements of L. So no matter how small you make epsilon, the other player can always pick an n that makes this happen. If that's the case, then the green part, the f of x, so that's the green part, right? This is my f of x, is approaching L as we're going to infinity. Okay, so this is a basic understanding of a function as x is going to infinity. Now you could reverse this whole drawing and make it go the other way. There's a similar definition that works for as x is going to negative infinity. Instead, the tube is going to go to the left of n instead of to the right. Okay, note that what's happening here is we're getting a horizontal asymptote. As the function is going off to infinity, it's approaching L, so L is a horizontal asymptote for this function. Okay, so the second concept that we get here is the limit not as x goes to infinity, but the limit as a function. As a function goes to infinity. So now, instead of the x value going off to infinity, the function itself is. So this is like the case where the limit as x approaches a of f of x is infinity, or the limit as x approaches a of f of x is equal to negative infinity. This is kind of what we're driving at here, right? You can also get a special case where you're doing both. X is going to infinity, then the function goes to infinity, so forth and so on. So in these cases, right, we have a for every L, which is an element of the reals, right? So if I pick a limit, there exists D, which is bigger than 0, such that if the distance from A to X is less than that delta, that number, so if I'm really close to X, then f of x has to be bigger than L. Okay, so as I'm getting close to A, this thing keeps exceeding whatever limit I give it. So then I get the limit as x approaches A of f of x is equal to infinity. So something like this would kind of look like, here's A, right? You get a vertical asymptote at A, and it's going off to infinity there and off to infinity there. And no matter how close I get to A, right? So if I get close to A, then ultimately I can always find something that's higher than the current L. Okay, so this is kind of going to make that vertical asymptote happen. There's a strange case here. So you can also do this with this thing going to negative infinity. It just has to go downward instead of going upward. Okay, so there's also a strange case here that we need to identify. Okay, so this is the case where where x is going off to infinity, and so is the function. So in this case, for every L, which is an element of the reals, so for every limit that I could possibly come up with, then there's going to exist an n. So we have, just like before, instead of a delta around an x value, we've got an n that we've got to be bigger than, such that if x is bigger than that n, then f of x also has to be bigger than that L. So we've kind of combined these two ideas. Then we say that the limit as x approaches infinity of f of x is equal to infinity. So if I kind of think about this a bit, I am picking an L value. So here's my L, right? There's my L value. And I have a function. And what's happening here is that every time I pick an L, I also have to pick an N, so that every part of that function above N, all of this, has to be now above the L line. Okay, so if you can give me an L, I can pick you an N that goes above that. If I can do that, then the limit as x approaches infinity of f of x is equal to infinity. So this is going to be the case that actually creates kind of a blowing up at the end. All right, so I promised also 3 limits that you have to memorize. Okay, today I'm going to give you these 3 limits. So this is what I'm going to call the 3 big limits that you have to memorize. And I'm going to give them to you without proof, but they're going to come up regularly in this class. And later on, I will prove all of them, but for today, we're just going to give them to you without proof. The first one is the limit as x approaches 0 of sine of x over x, which is also equal to the limit as x approaches 0 of x over sine of x. So this is the same limit because it can be flipped over, has to be equal to 1. So whenever you see this limit either this way or this way, it has to be equal to 1. Number 2, the limit as x approaches 0 of cosine of x minus 1 over x. Okay, so this guy is going to be equal to 0 all the time, all the time. You got to memorize that one. And number 3, now notice this one's slightly different. The limit as x approaches infinity of 1 plus 1 over x to the x. Okay, so this actually, I'm going to put a little extra tilde here, or actually I should do it this way. Put 2 dots here, because this is like really significant. This is actually a definition. So we're not going to actually prove this one, we're going to define this. This is what is E. So this is this Euler's constant thing, which is like approximately 2.717, so forth and so on. So this value is interesting. We'll take a look at it more extensively later, but this is the definition of Euler's constant, which we call E. All right, so today we've looked at the definition of a limit as x approaches infinity or negative infinity, the definition of a limit as the function approaches infinity or negative infinity. And we've also looked at 3 limits that you have to memorize, which is sine of x over x, or x over sine of x when going to 0 is 1, cosine of x minus 1 over x when x is going to 0 is 0, and the limit of 1 plus 1 over x to the x is defined as E, Euler's constant.